So let's move on to topic number 2 of the class. The topic number 2 is on stresses and strains and how they relate to each other. So when we talk about stresses and we talk about strains, uh, let's have one step back and let's think about any type of structure. So I think we settled the fact that I can have any structure possible. I could have a stapler, I could have an airplane, I could have, you got infinite choices and options. I could have a tripod. I can have anything I want to have. But everything, it comes down to when I want to design this, where is the location of the critical point? And that critical point is going to have maximum stresses. Uh, when we design something, we care for the location where that critical point is, because that location is going to have stresses that are very crucial or important. Okay, let me give you an example. So let's consider this hook, and we want to identify what the critical location is. And typically, you do this in finite element methods. And you can see this is, in this case, the scale goes from um, a blue being almost no stresses to red being maximum stresses. So if I was going to design this part, uh, if we were going to design it, just give me a second. Let me get my pen. If I was going to design it, I'm concerned about designing this location. Why? Because this is the location of highest stresses. That means if this point right here is safe, the whole structure will be safe. So sometimes the problem can be so cumbersome that we may divide it into parts, not to make it very thick. We can say, I'm going to take this segment, I'm going to take this segment, and I'm going to take this segment. And so all this segment will have certain dimensions, and this is going to have different dimensions, and this might have different dimensions or different materials even. But the fact is, if I identify the critical point here, let's say, that point will dictate the sizing of this entire structure. Maybe the critical point here is over here, then that will dictate the sizing of this entire structure. Maybe the critical point here is somewhere there, then that will dictate the sizing of this entire section. So that's why the critical location of the maximum stress is important. Now you can have tons of examples. As for an example, you can have the case of gears with a chain. So you can see how when you're designing the chain itself, it's going to have high stresses. When you're designing the gear itself, it's going to have high stresses. So this becomes very important. So that means my chain needs to be designed, my gears need to be designed to make sure that holds that. If I'm going to just take, in the case of a simple chain, you can see that these locations here are very crucial, but those are the location of maximum stresses. That means that these are the locations I want to strengthen, and I want to make sure either I'm going to choose I'm going to choose a combination of material, size, to make sure that point is critical. Okay, sometimes it's not even, it isn't just a complete design itself. So if you have the case of uh, a lifting elevator or something like this, you can see the high stresses are here. So by designing this bar at this location, everything else should be safe, because I decided, I showed that this is the location maximum stresses. How about the frame of the bicycle? Again, you can see that this is the location of maximum stresses. So that will dictate all the sizing of these bars, and this will dictate the sizing of this bar. This will dictate the sizing of this bar. And that's how we actually do it in finite element methods. That's how it's applied. In the case of airplanes, this is just another example. You can see how this location of high stresses become very critical. These locations become very critical in case of fire aircraft. So those are the locations where we typically, when we are designing something, we want to enforce and we want to make sure they are safe. Okay, so moving into the theory of what the stresses are, let's consider an arbitrary elastic body and let's chop that body in the middle. Okay, so I am not going to go into a whole lot of detail, but if I chop that, and by the way, this is in your textbook as well. Let me let me show you this for a moment. Let me find it. This represents. So if you go to your textbook, uh, just give me a sec. This is the same as figure 3.7 of your textbook. That's what we are trying to do. And the analysis, I'm going to have lots of loads, but at the end of the day, this is my resultant, and I want to know what the resultant is going to look like. You can show after some mathematics what happens when I take my delta A goes to 0. Delta A is this area right here. So if that area goes to 0, can you just imagine, can you guess what happens if this whole area goes to 0? This becomes what? It becomes a point. Thank you. So this becomes a point. So your entire equation, this whole equilibrium equation, is defined at a point. Okay, and you can pause the video for a moment and write this equation. That's very, very important. However, I'm going to move on, and from this is my, before I move on, this is my traction. This is what we call your traction forces. This is your traction. These are the tractions. This is your stress, and this is the unit normal in the surface. You can see it right there. So if you move on, what is very, 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 once again, let me stop so you can take notes. These are the traction, these are the stresses, this is unit normal. Okay, so in general, when you're going to do this kind of problems, this is what we call a state of stress. Okay, and the state of stress is going to have 9 components, as you can see, but it's a symmetric. By symmetric, it means that everything that happens on this side, right, about the diagonal is the perfect mirror. You can see that these are the same, these are the same, these are the same. Okay, they're identical. That means the matrix is symmetric. Some people call it, is technically talking about it. This is called a tensor, but this is in a nutshell. We can treat this as a matrix, and if we can show that these 9 components actually lead to somehow these are symmetric. This will lead to 6 unique stress components. Okay. So when you're studying and I ask you how many unique stresses do you need at any single point on any structure that you ever analyze? How many? Thank you. 6. Identically 6 unique stress points, stress components at any point. So when you're analyzing, let's say my plane, right? I care for a point there, and any point I'm going to have 6 stresses. Now, maybe some of stresses are 0, but that doesn't mean that they don't exist. They exist. They're the zero. They have a value 0. So that's why if you have the experience of doing finite element analysis, you can see that they will always give you a 6 stress component, so they will give the option for that. To better understand this, let's do something. Let's take that tiny point, that one point that actually is an infinitesimally small area. Since it's a point, I can make that point look like whatever I like to. To better understand this, what if I took that point equal like a cube? It can be a circle, it can be any shape. It's a point anyways. So let's see what happens if I take that point, if that point becomes a cube. Okay, and this is in your textbook once again. Is in section 3.3.8 of your textbook. Okay, it's right here. And what I want you to think about is the following. The notation that we typically use here is, so when you have your stress, the first subscript is the surface normal. The second subscript is the direction of. It's the direction of the stress. Okay? So what we are basically saying is, I have a cube, okay? I'm going to have stresses on this side, but I'm also going to have stresses opposite on the other side. This has to be in equilibrium. And then I'm going to have shear stresses here, and I'm going to have shear stress in the opposite direction because it has to be in equilibrium. So if I was going to do the following, just give me a sec. So if I was going to just look at my, let's say, if I see it from this side, right? I see it from my x. I can see that my cube actually looks like a square, okay? Where I say that this is my z direction, this is my x direction, and the stresses that you see there then would be sigma zz, yzz, the x on the z face in the z direction. Okay, and then the second one would be this x on the z face, so that's why this is z, and the second subscript is x, big x in the x direction. Okay, and then this has to be opposite on the other side to maintain equilibrium. Okay, and then we know that this has to go in this direction as well. Well, we can see it here, that x in the, now this tau x where? X in the x surface, you see? X in the x in the z direction. Okay, in this side, you can see it that it's going to act in the x in the z direction. Okay, now I told you already. Okay, before I move on, I also have sigma xx. I also have sigma xx. So I already told you that these two are equal to each other because we are working a symmetric case. Okay, now this looks very familiar because, you know, in strength of mechanics of material, you often had stresses like this, right? They always showed you this case, and you had stresses, you had what you call a stress element. But that stress element depends on what direction you're seeing. In this case, I'm seeing this from the y direction. Sometimes it's seen from the x direction. Sometimes it's seen from the z direction. Okay, so let's consider various cases. So what happened if I take the same thing I took my same case now, and let's go and see it from the z direction. Let's see it from top. Okay, so if I see it from top, okay, if you see it from top, you can see that my y goes in this direction and my x goes in this direction. So in this, so when I'm seeing it from top, I have a stress that acts in the y is y, yy. So this is yy. And also I have the equilibrium stress on the other side to maintain this in equilibrium. Okay. So I also have a stress acting in the y direction, in the y phase, a surface in the x direction. That means I have a stress acting in this direction that will be tau y x. Now, if I go and I'm seeing it from the top, remember, I'm seeing it from here, then you're gonna see this surface, and then you're gonna see this one acting in the x and the y direction. Okay, so then you also have this one acting in the x and the y direction. And because of symmetry, this happens the same on the opposite side as well. This is tau xy. This is tau yx. Now, then you're also going to see that you have your normal stresses. That look like this. And as I mentioned before, because of action, because of a symmetry condition, these two are equal to each other. Okay, so we could do the same thing, seeing it from the x direction. I will leave that for your quiz. Okay, so now this is my state of stress. To better understand how this works, let's do a simple example. Okay, but before we do that, yeah, let's do a simple understanding on how this really works. Suppose I have a state of stress that actually looks something like this: 10, minus 10, 0, minus 10, 0, 0, 5, 0, 0. Remember, to first check, make sure this is symmetric. And it is, so we can move on. And I said, draw this in this cube. Well, if you did this in this cube, this is what will really happen. So I draw my cube. Okay. And if you remember from here, it just tells you the values. So the first value, sigma xx, it says has a value of 10. Okay, so that means this is my x-axis. Okay, I'm looking at this figure, x. So it's saying x in the x phase, in the x direction, and it's positive. So it's going to add like this is 10. Okay, obviously then you have in the opposite direction as well, which I'm not going to draw here. Then you have minus 10. This is in the x direction, in the y-axis. So it should go in this direction. However, it's negative. So negative means that it actually goes in the opposite direction. So it goes 10. Okay, and then you have zeros. So that means this is 0, this is 0, this is 0, this is 0. You don't have to worry about this because it's a symmetric matrix. You have this one. So this one in particular is in the z plane, in the z phase, in the z direction, and it's positive 5. So it's 5. Remember, you have loads in the opposite directions. So if I can draw this, I'm going to have 10 on the opposite side. Also, I'm going to have 10 in the opposite side, and this is 5 because my problem has to be symmetric. That's what we mean by this. Okay? Now, I want you to stop for a moment and I want you to think. Um, Typically, when we do aerospace structures, we do machine design, we do any structure, can be civil engineering, can be submarine. We care for stresses at a point. Now, from all those stresses that I have there, the question is, how do I determine which stress to use? Um, if I have, let's say, my famous stapler, right? I get a finite element method might give me my critical point, but that critical point has so many stresses, has X, Y, Z, all three components, tau X, Y, tau Y, Z, tau X, Z. So which one do I use for my design? Anyone want to give a shot? What do you think? Thank you. So first of all, it's kind of hard to understand which of those 6 stresses I'm going to use. So typically we want to use something we call principal stresses. Why we care for principal stresses? Because the principal stresses tell me a point for the same loading condition, same boundary conditions, same material, same thing. I'm just taking the structure. If I rotate that structure, the structure is rotated, that point in any given rotation is going to have the following maximum possible stresses. So that means if I design for those maximum stresses, it will never fail, right? So that's what we want to know. That's what we are always interested in, finding principal stresses. Typically, you are used to doing this using Mohr circle. Now, although there are benefits of the Mohr circle, in the old days, we didn't have computers, we didn't have calculators, so you are relying basically, you are stuck with a ruler. So the Mohr circle became very handy. Nowadays, really, with all the computer and software that we have, you can find all these values using MATLAB. I'm going to give you reverse engineering how to do the Mohr circle with the principal stresses that MATLAB will actually give you. Because I think the Mohr circle does give us some very nice and neat insight into the problems, to what's the behavior of them, what happens, but we're going to do reverse engineering. Okay, so let's move on. So in order to find that, the big question is, how do I do it? So I wanted to consider the case. This is nothing else than an eigenvalue problem. And we are not going to go into details on how these eigenvalue problems actually work. We basically multiply this by minus lambda, and we want to make sure this is 0. Now this is my unit vector. The unit vector, my unit vector can never be 1, can never be 0. It's always equal to 1, right? That's the basics. If I take the norm of my unit vector, right, you will get this is equal to 1. So that cannot be 0. The only other alternative I have is if I take the determinant of this equation to 0. Okay. So we can do that. We can take the determinant of this equation and set it to 0. And that equation is identical as your textbook. Your textbook has that equation 3.15. It's right here. See this equation? This equation is equivalent to what I am giving you. It's the same equation. Okay? But I'm just probably breaking it down a little bit more so it helps you to understand this. So I express this equation in the following manner. This is called a characteristic equation. And again, where does this equation come from? It comes from taking the determinant of this. Okay? So when we do this, and knowing the fact that these are symmetric, you can simplify to this and you can simplify to this. Okay? So the problem here is the problem reduces to finding these guys, and these are called stress invariants. Okay? This is the first stress invariant. This is the second stress invariant, and this is the third stress invariant. Okay, so if I ask you, and you can pause here and take notes, so you write this, I want you to write it by hand, these equations in your note. You don't have to really write all of this, you really need to write the final answer, these answers right here. But I am going to continue my discussion. You may pause, write, and continue. So I want you to think about this. When I talk about invariant, what comes to your mind? Invariant comes something that doesn't vary, doesn't change. So it means that just like you and I have a social security number, it's a characteristics of me, it's a characteristic of somebody, and my fingerprints, I'm the only human being on earth that has that same fingerprints. You can think about these eigenvalues or these principal stresses, this stress invariance, actually meaning that those are characteristics of that one point. Remember, stresses are defined at that point. We analyze everything at that point. We find the loads at the point. We want stresses at the point. We design points. That's what we do. So at that one point that we decide that's critical, these stresses are going to represent the invariant the stress invariance represent stress is the value characteristic of that point and do not change. Okay, they will not change given that problem they have. So these are called stress invariants. So if we move on to the discussion, well, the solution to that, and again, I know this is cumbersome. I am not asking you guys to do this by hand at all. You can just use MATLAB for this case. Most of the problems, if you have to do them by hand, they are 2 by 2 and quadratic equation, which we will go over that in the next lecture. So if you did something like this and you were to solve it by hand, this is the solution to that. Now, this will give me my principal stresses. And I want you to think for a moment. If this equation was all a function of stress invariance, right? Then what can I say about my principal stresses? This is invariant, this is invariant, this is invariant, and this is beta is all a function of invariant stresses, so this is invariant. So then you can say my principal stresses are also invariant. Very good. They are function of that variant at the point. Okay? The characteristics of the point. They tell me what happens to that point. Okay? So this is not, so once we have that, we want everything in our normal sense. Okay? And this is from, again, from your textbook, is right here. You want to order them sigma 1 bigger than sigma 2 bigger than sigma 3. So you always want the stresses like this. So once you find your principal stresses, you have to order them. You have to make sure that always sigma 1 is the maximum, sigma 2 is sigma 3 is the smallest, and this is whatever's left. So let's say as an example, I got lambda 1 equal to minus 100. Lambda 1 equal to 10, lambda 2 equal to 0, lambda 3 equal to minus 100. So sigma 1 is going to be the maximum of this. Remember, this is minimum because it's minus. So yes, you take into consideration the sign. So this is 10. Sigma 3 will be the smallest of these. That will be minus 100. And then sigma 2 will be the remaining, is 0. Okay? That's how we will always use this. So I will never like to see anyone say, oh, this is sigma 1, this is sigma 2, sigma 3. No, these are your principal stresses that you form from your calculations. But now you need to place them in our normal order, sigma 1, sigma 2, and sigma 3. Okay? So this basically wraps up the first topic I wanted to discuss with you. And following this, you will see some examples that will be helpful to understand and disseminate this material.